All right, so we're going to start talking about some concepts when you involve interpreting distributions based off of their mean and center. So distributions can look all sorts of different ways. You could have, a completely even distribution. Everything is just nice and flat. This is one that's possible. You could have one that is normally distributed, which is going to look something like this. You could have one that is right skewed, which is going to be very heavy at first and then taper off. Or you could have one that starts off really low and then tapers off towards the end. So distributions could have all sorts of different looks. And over time, what we've really tried to focus on is how do we see and how do we predict where certain data is going to be, how much data is in a certain place. That's what we're looking for. And so this is going to help us predict things later on and to make determinations. Well, the first person to really try to describe the percentage of data in a distribution was this guy named Chebyshev. And this is, if we do not know what it looks like. So let's say, in that last picture, the last graph I showed you, or slide, excuse me, we know what these look like. I just drew them, right? But what if we don't know? What if we don't know what they look like? Well, what he has is a general rule, which is written as such. That if I know k equaling the number of standard deviations from the mean. So this is just some number. So like, for example, let's say I had, my mean is here. Let's say my mean, we'll just call it 50. And we'll call my standard deviation, we'll call it 10. Okay, well, let's say I have this particular distribution and I'm just doing this for fun. So this is my mean. Well, if I go 10 in each direction, so minus 10 and plus 10, this would be 1 standard deviation above and below. So k would be 1. Now if I did this again, minus 10 plus 10, I'm now at 2 standard deviations above and below. So this is 2 above and 2 below. So we're looking at this range in the middle. So we're trying to use all this information to predict how much stuff is in between. Well, Chebyshev's rule only tells us at least this amount will be there. Okay, so first off, we have our first number. Or excuse me, let's write our formula first. So it's going to be 100 times 1 minus 1 over k squared, and that will be our percentage. So the k being the number of standard deviations from the mean, we can make a chart to say at least this percentage of data will be within that range. So you have the chart there, but I'm just going to do a few for you so you can see where this numbers come from. So let's say if k equals 1, excuse me, let me write this a little bit bigger. K equals 1. So 1 standard deviation away, left and right of our mean. So how much data, at minimum, are we going to have there? Well, if we do 100 times 1 over 1 divided by 1 squared, and the percentage of that, well, this is 0%. Well, that's not very helpful, is it? And it's saying that at least 0% of our data is within 1 standard deviation of the mean. Well, that makes complete sense. There should be at least 0% if the average is there. So it's not super helpful for that. But when we say, well, what about within 2 standard deviations? Again, realize that this is when we don't know what it looks like at all. If we do this for 2 standard deviations, we end up getting 100 times 1 minus a fourth, or this is 3/4, which if you do the math, this would give you 75%. So at least 75% of the data is within 2 standard deviations. Now k is 3, end up with 100 times 1 minus 1 over 3 squared, which this should give us 8/9 times 100, so this should be like 89%-ish. So about 89% live within this, and so on and so forth, and you can keep going down the line and saying that, within this number of standard deviations, you have this percent of data. So this is more of a minimum percentage within these amounts. Now the empirical rule is much more useful for us because we are judging this versus the normal curve. So this is the normal curve. So the normal curve, remember, is our nice, perfectly symmetric little bell curve. Now, if I make my nice, perfectly symmetric little bell curve, okay, it's pretty good. I'm not a great artist, but you see that? I will have a mean and a standard deviation. Now, if I go one standard deviation, so one standard deviation above and one standard deviation below my mean, how much data will be there? Well, within one, I'm going to have 68%. Okay, so symmetrically, it would make sense that each side gets 34% of that because it's perfectly symmetric. Remember this. It's very important for us to understand how this works. So within one standard deviation, we have 68% of our data. Now, within two standard deviations, so plus one standard deviation, minus one standard deviation, within two, we're going to have 95%. And this is based on the empirical rule, so this is for the normal curves. It's different than Chebyshev's. But if we have a normal curve, then within two, we're going to have 95%. So we already have 68% taken care of. So if we think about this, we've got 95%. We take away 65%. So the amount of new population, or new population that we should have here, oh, excuse me, that should be 68. That is going to be 27%. So 27% will go into here and here. Now, again, just like what I did before, I have to split it up. So each of these is going to get 13.5%. So these percentages reflect the amount of the population that will be found in these little zones. So, for example, the percentage of people between the mean and one standard deviation above the mean is going to be 34%. Okay? Where, if I wanted to know the percent of the population between one standard deviation and two standard deviations above the mean, that would be 13.5. So there's all different ways we can look at it, but that's the beginning here. Now, this, I'm going to erase this real quick. Our last little section here is going to be within three standard deviations, we're guaranteed to have 99.7% of our data. So if we go, and this is not perfectly drawn, by the way, so it's just for illustrative purposes. Within three standard deviations of the mean, so all the way, this whole section here is going to make 99.7%. So, but these new ranges are going to have far less. You can see that just based on the size, it's going to be a lot smaller. So if we do like we did last time, so 99.7%, and we subtract away our 95%, that is going to give us 4.7%, which if we divide that into 2, we will get 2.35% into each of these. Now, obviously, there's still some left over, right? We still have 0.3%, and those are going to be below down here and above up here. So this can go on and on and on and on and on and on forever. You never quite get to 100%. I mean, because you could literally have observations that are super high or super low. So you'll never see it get to 100%, but it'll get very, very, very close. But this is the idea behind what the normal curve is. Now, the last thing we're going to talk about are z-scores and percentiles. So what a z-score is that's going to be our observation minus our mean divided by, or excuse me, mean divided by the number, or the whatever our standard deviation is. Okay, that's what a z-score is going to be. So, for example, let's say if I had a mean, let's say that the average age of an American is 45 years old. Or 45 years. And let's say that our standard deviation is going to be 5 years. Okay? Now this is just data I'm making up. Well, if I wanted to know a z-score, and a z-score is important because it gives us direction in our distribution. And it tells us a lot of other things too. But let's say that, I'm 28. Okay? So in this case, what I would do is I would do, to find my z-score, I would do 28 minus 45 over 5. So this is going to be negative 17 over 5, which that's okay, negative 17 over 5. And this is going to be negative 3.4. Now, this data is obviously just made up, but this negative 3.4, what it tells me is it's the number of standard deviations above or below the mean. Now, obviously, the negative indicates that I am below the mean. Okay? Now, positive would mean that I'm above the mean. And then the number here is how far above and below it I am. Now, what's important here is that this number tells us, this number will correspond to the normal curve the same way that it would be if it was a positive. It's that far away. So if we look, a positive 3.4 would be all the way over here. And a negative 3.4 would be all the way over here. Just like a positive 1, let's see here. A positive 1 would be right here. A negative 1 would be right here. So there's a symmetry to it. And so we use these z-scores as a way to find out about where we are on our normal curve. Now, for percentiles, and sorry, I'm going to draw this all the way down here because I've run out of room. Percentiles are going to be at which endpoint will I have or what is the percent of people below my percentile score? So for example, the mean is going to be the 50th percentile. Or the, 50th percentile. So if we go back, this is at 50% because 50% is below my number. Now, if I wanted to do, let's say, a z-score of 1, z-score of 1, what percentile would that be? Well, let's go back to our normal curve real quick. So a z-score of 1 is this right here. So which percentage of our population is below that number? Well, let's think. We know that this is 50%, or the 50th percentile. Well, on top of that, we have 34 more percent. So this would be the 84th percentile. And what about a z-score of negative 1? What would a z-score of negative 1 be? Well, a z-score of negative 1 would be right here, so we're 1 below the mean. Okay, so we know that this is 50%, right? We know that this is at the 50. And we know that this z-score is 34% lower than that. So 34% lower than that is going to be the 16th percentile. So what this tells us the percentile scores and how everything works is that the amount that's below our mean. But the main thing is with the normal curve is that you can see that within just 1%, or excuse me, one z-score of the mean, so one to the right and one to the left, we have this huge proportion of people. More than 2/3 are within one standard deviation of the mean. So most people tend to be around average. Fewer people tend to be that much above average or that far below. But there is a symmetry to the way all of this works.